Okay, so let's start. So you should be seeing my slides now. And here we go. So this is the second class in this series, and we'll be talking about stuff today that might seem quite low level still, but I think it is important not to omit it because even though it looks low level and rather technical, for most part it is something that is inherently present in anything multilingual that we can do with language these days. And sometimes if people are not aware of various like encoding issues, then they might draw wrong conclusions, or even like think that they have developed something that's multilingual while it's not. So it will actually have roughly two parts. In the first part, I will be talking about language identification, and the second part will be even more low level than that one, because that will be about various character encodings and Unicode. So, sorry. Language recognition or language identification, language ID is often the label for the task. Uh, it is something that's uh, already relying on some sort of machine learning, depending on how deep you want to go with that. Uh, so it's not just a few low-level heuristics. Uh, but it's reasonable. It's a reasonably simple task for the most part. At least if you have a reasonably sized document, it is usually, and if it's not code switching, if it's just one language, then it's usually not so difficult to automatically estimate what language the document is written in. And that's actually a very useful task, or very useful tool if you have such a tool that can recognize it. Because obviously, if you want to process language, you need a lot of data. Quite often the data comes from the web, because there's plenty of language data available just for you to grab it. But then on the web, you are never sure what language you have. If you crawl the web and you follow the links, you can pretty quickly arrive at a website which is in a different language than the one where you started. So you need to be able to sort it out. Because if you want to be focusing on one of the languages, you need to be able to, with certain level of certainty, to say that it's actually the language you're looking for. So the language recognition can happen at various levels, actually. Normally, or at least for the motivation that I was talking about, it's at document level. So that means that you just need to, you have a document, you have a file, and you need to find out whether it's in the language that you're looking for. Then the second level might be something like a paragraph or sentence level. And sometimes you even need to find out within one sentence if you have a code switching document or something like that. So those additional levels are actually more difficult. The less text you have, the more difficult it is to find out what language you are actually dealing with. So we will be mostly assuming that you have a large document, but essentially the methods will be the same. Just you will need to be more precise and with fewer text or little text, it will be more difficult to get reasonable precision. So essentially what you could do, obviously the first thing that you will probably think of if you are to recognize language, let's look at the dictionary, and if we see frequently enough words from that language, then it's the language. However, that's not so easy, because you don't always have dictionaries readily available. If you have them, then great, you can use them. But if you need uh, a language ID for many different languages, then you need many different dictionaries. If you want to acquire them, then you will need actually large data to obtain it. So you will actually have to crawl the web first, unless you have a corpus for that language or something where you are sure that it's the language you're looking for. And even then, there will be problems with coverage, because not no dictionary has all the words from the language. So there are actually methods that are easier than that, and those methods don't look directly at words, but at smaller units, which usually means characters. So here is like a motivation example. If you look at, if you see a line of Hebrew text, then you immediately know it doesn't look like any European language. Or, well, if we count Yiddish as a European language, then it could, but anyway, it's a different script. So that's one clue. If the language uses a script that's unique enough, then you can rule out many other languages. But that's often not the case. Anyway, if we are looking at the characters, there are sometimes characters that are unique to a language. So for instance, if you see R, then it's quite likely that you are looking at a Czech word. If you see this /O, then it's quite probably Danish or Norwegian. And there will be some other similar letters that are specific to one or the other language. But unfortunately, there are languages that have no specific letters, and many letters are shared with other languages. And probably most importantly, if you see a specific character in a text, there's no guarantee that you are actually seeing a text in that language. It could be just one word, like this last sentence here: Die Burg wurde vom böhmischen König Przemysl erobert. So this is something that could be from Wikipedia, for instance, where you often have really the original diacritics in loan words or foreign names. So yes, the name is Czech, but the sentence overall is German. So this alone will not help you. So we need something more than just looking at one word or one character. So what about looking at character frequencies? We could look at multiple characters, or all the characters, the whole alphabet, I would say, of the language. But in case of looking at a document, it actually means that all the characters that you find in a document, and order them according to their frequencies. So this is an experiment that I really did many years ago on sample texts that I had for 7 languages. And the first 5 letters on each line are the most frequent letters for that language, or for the document in that language. And the second 5 letters are the the least frequent ones. So here we can see that there are some letters that are specific to those languages, like the j in Czech and Slovak. But unfortunately, those specific letters are also quite infrequent, even in the languages for which they are specific. Which also means that the frequencies with which we see them are quite unreliable, because you need large numbers to have some confidence that they represent something. So in fact, what is more interesting is actually the letters that are not so specific. Like if you see in Slavic languages, O is often the most frequent letter, while in Germanic and Romance languages, it's not the case. It's usually E. And again, this letter alone will not tell you enough, but if you look at the others and get something like a histogram of the frequencies, then it will tell you something. Then you will be able to recognize that the languages are slightly different. So you can actually look at, you can take the relative frequencies of every letter in the language, where language for you is represented by a training data set, but the training data set doesn't have to be large. That's the advantage over using a dictionary. You just need a reasonably large document. One document would be enough if it has, I'm now just guessing, but if it has, let's say, 1,000 words, then it will already tell you something. And for each, so relative frequency is a number between 0 and 1. So that's a value for each letter. And you can have all the letters, so that's the frequencies of them put together. That's a vector of a size that corresponds to the size of the alphabet. So for many languages, it will be something between 20 and 50 letters. A problem will be obviously languages like Chinese and Japanese, but those are pretty easily recognizable anyway. And so you get a vector, and you can get a similar vector for the test document, which you want to identify the language for. And then you have two vectors, and essentially if they are identical, then you are pretty sure it's the language, and they will not be identical, but you can measure their distance somehow. There are many different metrics that you can use. So I have one example here, and you can invert it to get something like vector similarity, but it doesn't really hugely matter which metric you choose. You just need to be able to have something that will tell you these are more distant than those, and that's it. Then the question is, what do you do with the similarity metrics? Well, if it's or distance metrics, depending if it's similarity, then one possible approach is, if it is larger than a threshold, then you say these the languages of the two documents are the same. And the second option, you don't know the thresholds, obviously. You would have to test it for your concrete metric on data and see what seems like a reasonable threshold. The other possible approach is that you try something like training on all existing languages. Obviously, we will not have all the languages, if nothing else, then because we don't know what the exact list of languages in the world are. But you can collect data for dozens of languages, and then you can be, and especially if you know that you are downloading data from like larger websites, then you are probably not likely to get other languages, and you are probably looking for one particular language, so you will make sure that that language is represented well in your data set, but you may have a number of other possibilities. And then you will find the closest language, and you will always give an answer. So if there's a language that you don't know, then you will instead you will have an error. You will instead say it's some other language that seems to be closest to that one. Now, the obvious question is, where do you get sufficient data for training on many languages, if not all? And there are some possibilities. So for a long time, I've been experimenting with the Universal Declaration of Human Rights, which is available at the United Nations website, a collection. Some of them cannot be used so easily because they are just scans of handwritten Kashmiri script or something, but many of them are available in Unicode encoding, so you can download a text document and train on it. And it's translation of the same document for other languages, which is interesting enough and useful. On the other hand, there is limited vocabulary, obviously. But if we just look at characters, that might be enough. The other possibility, much larger possibility, is the translations of the Bible, which are also, many of them are available online. And there are other options. There's also the Watchtower corpus, where the Jehovah's Witnesses produce a lot of text and translated to many different languages. So I don't think they really do it to make it easier for us researchers to train on languages, but nevertheless, the data is available online. and then obviously there's Wikipedia. So those are just a few quite obvious sources of multilingual texts where you can train a lot of models. Now, so far I've been talking just about frequencies of individual characters, but in fact it might be more precise or more useful if you look at uh, sequences of characters from the text, like character trigrams, for instance, which will reveal something more. And I want to argue that they are sufficiently revealing even for a human. Even if I just show you a few most frequent trigrams of characters from a language, then it's quite possible that you will be able to say what language it is just based on your previous experience with the languages. And even if you don't speak the language, I mean, if you've seen some text in that language, it's quite possible that you'll be able to recognize it. So if we were in the classroom now, I would probably ask you just to shout what do you think it is, and then we would discuss it. Since we are now in this distant mode and we are recording it, I'm not asking you to react aloud in any way, but I will just give you a few seconds for each example. I think I have like 10 examples here, and you can take notes and note down your guesses what languages it is they are, and then I will show you the correct answer. So this is the first language. Here's the second example, number 3, 4, 5, 6, 8. So sometimes maybe you change your mind when you saw another one, since obviously every line has a different language there. I have one more which is quite special, so I will discuss it when I show you the correct answers. So here you go. It was German, Dutch, English, Slovak, Czech, Hungarian, Polish, Italian, Spanish, French, and Russian. So at least my previous experience from the classrooms in the previous years says that usually the Romance languages are much more difficult to tell apart, at least for the audience that we get here in Prague. I actually, in most or almost all lines, these are really the first 6 most frequent trigrams that I found in the text. There was one, I think one exception, that for Italian I wanted to make this zio appear here, because it was I think it was 7th or 8th, and I thought myself that Italian was difficult to distinguish from Spanish and French. Anyway, the last line, that's interesting, that's how I highlighted it here, is that if you don't pay enough attention to the encoding of your text, and especially if you get it from the internet, then it's quite possible that you will get things like this: the entities that encode some diacriticized letters, especially from the Western Europe. So this is the accented A in Spanish, the what would be long A in Czech and Slovak, like A acute. And because there is also the other vowels with acute accent, so this is a relatively frequent sequence of letters that appears in the HTML page. And if you don't decode these to the real letters, then you will get ute, aku, and kut many times in the text, and it will not tell you anything about Spanish. It will tell you that you have HTML entities in there. So this is one warning that you have to look into your data and see what's there, and don't forget things like this. Now, there's one more interesting update of this approach, and that's adding word boundaries to the to the alphabet, because quite often a particular n-gram of characters is frequent at the beginning or at the end of the word, because those are frequent affixes in the language, prefixes or suffixes. So here we see the modification. If I include the word boundaries in the alphabet, for German, for instance, now an at the end of the word is very frequent, more frequent than sh as ch. And er is another suffix. There's no frequent prefix. I think suffixes in these languages will be much more prevalent in the frequent trigrams. So here we have for Dutch and for English, and here for Slovak we already have even some prefixes. So pr standing for pre and pre, I would guess, and pro. That's the most frequent prefix. Po, ne, that's the negative prefix as well. For Czech, it's slightly different, but there are some repetitions. Hungarian, and so on. Now, I said in the beginning that we will not use the dictionary because it's difficult to obtain, and we will look at characters instead of words. But in fact, words are still somehow hidden in the model that we get this way, simply because if you have a frequent word, then it will contribute frequent character trigrams to your model. If you just look at a text and take one character after the other, you will see the prefixes that are in frequent words will be frequently there. So for on the one hand, word frequency is another feature of the language. So it's not a bad thing in principle to have it there. But the problem we get with it is that the data is sparse. I've been telling you that we normally don't need a very large training data set to train this model, but we actually, even if we have large enough document for training, we also will be collecting the frequencies for the test document, and that might be pretty short. So inherently, we will not see enough words in the target. And if the target document is about a specific domain, then it might be that the most frequent word is quite different from the most frequent word that was in the training data. So the frequent words actually do affect the frequencies, but they are more characteristic of the domain or the text topic, and not necessarily always about the language itself. So we will see some examples in a few seconds. So the UDHR, the Universal Declaration of Human Rights, is relatively small, so there is already some problem, and that's the training data. It's not yet the test document. So here is the example. In the Universal Declaration of Human Rights, in the Czech version, právo, povinnost, and poslání are the I wouldn't say most frequent words. Most frequent would be some conjunctions, but they are very frequent. They are probably the most frequent nouns. And if you look at the excerpts from the Slavic translations of the Universal Declaration, you can see pretty easily that there are repeating patterns. There are the similar words with similar prefixes and suffixes, and obviously there are the same trigrams repeating, even if not at the same in the same order. So we can see that these that the models trained on the Universal Declaration of Human Rights will be biased because of the topic and because of the frequent nouns that are there. It's even more visible if you look at one particular website and try to collect the vectors on that website, so to be able to say what language the website is in. So I did this experiment many years ago. So these days you would get a different outcome there, but you could try it elsewhere. Centrum CZ, Czech web portal. When I try to just download the title page and collect the words that were there, so after dismissing all the HTML markup, I got Praha as the most frequent word, just because there was a drop-down menu trying to sell you some sort of advertisements, and there was your location. You could select your location, and it was Praha 1 to Praha 15. So that makes Praha the most frequent word, but most frequent here means that it was there 15 times, period. So obviously it's not the same. It's not representative enough. By chance, PRA is here, and it will be probably somewhere here as well. Okay, we have it's not the same as PR long A, but it probably will be frequent enough, but it will be very biased. So we have to do something about it. Here is the opposite example. Prague dependency tree bank. It's a 1 million word corpus. And if we collect trigrams on that data, we will see that it's again different, not just from Centrum CZ, but also from the Universal Declaration of Human Rights. So there's actually just OST is one suffix that appears here and there as well. Then here there's NOS. It's the other that we see in the first 6 from the Universal Declaration of Human Rights, and otherwise it's different. So here is another angle of viewing it. Now I'm showing you the most frequent words from the Prague dependency tree bank, and these are pretty close to what you would see at any publication about Czech, which would list the most frequent words in the language overall. So these are stop words, all of them. There are conjunctions, prepositions, and similar stuff, auxiliaries. If you look at the Universal Declaration of Human Rights, the most frequent words, there is still the conjunction a as the first most frequent word, but then pravo, the right, is immediately the second one. Then we have a preposition, a conjunction, a very frequent verb, and článek, that's article. That's again something that's very specific to this topic, and so on. So it is already quite different. If you look at Centrum CZ, then you see that Praha is the first word, Čeština, you can select the language there, and I think most of these words were actually just once there. So they are, I list them as most frequent, but they are, there were not too many other words. So there is, fortunately, a way of mitigating this pretty easily. You just count every word type only once, and then your statistics will be more representative of how the language behaves, especially if the language has certain patterns, or the orthography of the language has certain patterns that repeat, or if they are repeating suffixes, prefixes, then you will get really a glimpse of those affixes and not of the word that is by accident most frequent for your document. So if we look at the Prague dependency tree bank, the change is not huge. The lists are not the same, obviously, but some of the trigrams are still there, like Ost, they just change their order, Ova, and so on. So it's not a huge deal. These are still representative quite well, both of them. For Universal Declaration of Human Rights, you get Ost, A, Ninos, Any. These are more affixes than just stems of the frequent words. And even for Centrum CZ, even though it's not a miracle, because you can get miracles from just a few words, it is still, I would claim, at least like intuitively as a native speaker, I would say that these are more representative of the language than the ones in the upper line. So that's almost all I had to say about language identification. I have to speed up because I'm a bit slow today. There is a bridge to the second second topic, and that's character encoding. I've been silent about it so far, but what to do if your documents are in different encodings? So essentially, if ideally you should have Unicode, and meaning encoded in UTF-8 everywhere, but maybe you don't know the encoding. If you know it, then you can convert it to the same encoding, and then you can convert, and then you can compare just the languages. A side note is that on Unix, there's a command file that can quite often guess what type of file you are looking at and what encoding it uses. So sometimes it can guess it. It's not always 100% correct, but usually it is. If you don't know what encoding you have, then you can deal with it as if different encodings were a different language, and then you can train models for all encodings that you are expecting, and see what you get. Here is a sample of encodings. Most of them are now historic, because you will these days you will probably, for Czech, you will find the code page 1250 on Windows, and sometimes ISO outside Windows. UTF-8 is pretty much the standard these days, or it might be ASCII without the diacritics. And I'm saying I'm showing you different encodings here for the first 6 or 7 trigrams, but in some way it's actually cheating, because I should be showing you the byte numbers, because here I'm showing you the graphical form of the glyphs, and that's again depending on what font you use and what encoding you use. So this is how you would see those different encodings if you had an editor in Windows, in Czech Windows, with the first code page. So that's why the first line shows the real appearance of the trigrams, and the other lines look scrambled a bit. So Unicode, as I said, if we can use everywhere Unicode, it's the best thing we can do, even though it has its downsides as well, but at least we can encode almost all the languages of the world. So originally, which means early 1990s, it was designed as a 16-bit code to replace the various 8-bit code pages that existed up to that time, and that were actually that was what you had to recode every time you were dealing with a different language. And later they found out that even those 65,000 characters that are available in Unicode are not enough. So it was enlarged in later versions. One possibility of looking at it is it's a fixed width encoding. So you will have 2 bytes everywhere, at least until they've added additional characters. And you could use UTF-6, what they call UTF-16. So you always have 2 bytes, and it's a number between 0 and 65,000 something. Later on, 11 years later, they came up with a version that needs 32 bits. In fact, they don't use it all, so they only use something like 1 million characters, but obviously it's much larger than it was previously. So again, you could encode it using always 4 bytes or 32 bits with UTF-32. But the usual way of using it is UTF-8, and I will show you what it means in a few seconds. Just a short sample of what kinds of characters there are in the additional blocks of Unicode. So besides additional alphabets like the ancient Egyptian hieroglyphs, you will also find things like Byzantine musical symbol psili and domino tile horizontal back 0606 and so on. So there are really sometimes quite bizarre types of characters available. I say currently it was 4 years ago when I was preparing these slides, so it's certainly different today. Unicode version 10 had actual 136,000 characters from 139 languages or language script pairs. So it will be larger now. So you can see they have reserved a space of 1 million characters, but still they are far from using it all. So what is UTF-8? It's a way of encoding Unicode. So that means we still have that code page of roughly 1 million possible code points, but there is a variable width of character in terms of bytes that you use. So that for the most frequent letters of English alphabet, you need only 1 byte. And for less frequent or larger alphabets, you will need more than that. So that's the encoding that I would suggest you use everywhere in your data and in all your software. And if you can ensure that, you will spare a lot of effort, a lot of headache with converting encodings. So I said this already. So for Chinese characters, for instance, you will need 3 or even 4 bytes in UTF-8. How does it work? If you use out of the 8 bits in the first byte, if you use the first 7 bits and the 8-bit is empty, so you have possible codes 0 to 127, then it's just 1 byte code. You don't need more bytes for that character. So the entire English alphabet can fit in this, for instance, and some of the old ASCII punctuation symbols as well. For larger for higher code points like 128 to 2000 something, you need 2 bytes. From 2048 to 65,000, you need 3 bytes. And for the additional blocks, you need more than that. So how does that work? The first byte will tell you how many bytes there are in total. So if the n highest bits are set, it means n bytes are the total size of the character. Then there is a 0, and after that 0, the actual code starts. So you can look at the byte, at any byte in the text, and if it starts with 0, it's 1 byte. If it starts with 1010, it's a non-first byte of a sequence, and the others are first bytes of longer sequences. So that also means, that means 2 things. We can always recognize where the character starts. That's important. But it also means that not every byte sequence is a valid UTF-8. That's different from any character encoding that existed before that, because you could always recode it as something else. You could just take a different font, and if you had 8-bit encoding in Windows, and then you saw it in I don't know in Unix, and you knew you had something, you had a bad font, but at least the sequence was always valid. It was not invalid. In UTF-8, it's no longer the case. Here is an example of how it works. So that's the capital Ch from the Czech and Slovak and some other Slavic alphabets. And its code in Unicode is 268, or in binary, it's 9 bits in this sequence. So 268 is in the second block, so we need 2 bytes. And the first byte will have to start with 110 to say that there are 2 bytes together. The second start with 10 because it's a non-first byte. So we have already used 5 bits of the total space we have, and we have 11 bits available for our actual code. And because we only need 9 bits, because this is 9 position binary number, we will pad them with 2 zeros from the left. So this is the result. We have the red ones are the control bits, and the black ones is the actual code. And then when we look at it in hexadecimal encoding, then we get something like this. So that also means that neighboring letters from like the Czech alphabet, which are accented, will often have the higher byte the same. So that's why they you will often see the repeating strange letters if you look at UTF-8 as if it was some other encoding. So now briefly about Unicode itself. An interesting part of Unicode is that there are various properties of each letter, and one of them is or each character, and one of them is the category, and you can query them. So there is a category of letters, and that means not just Latin letters, but also Cyrillic and Greek and Arabic and whatever. I think this is Tamil and Chinese characters are also letters. Then there are marks, various diacritical marks if they have their own code point, which you can combine with other letters. Numbers, again, not just the Arabic or Western Arabic numbers, but also Eastern Arabic and various index scripts and so on. Punctuation, again, even punctuation is not just the one that we know from European languages, but other types as well. Various symbols, thousands of them, not just currency symbols, but various icons and mathematical symbols. Separators, and interestingly, things like zero with non-joiner. There are a few characters which don't have any visual appearance by themselves, but they affect the overall appearance of the word. So zero with non-joiner is something that in some languages you will see it pretty frequently, and it is part of the word. So for instance, in Persian, according to the standard, you are supposed to use it before the plural suffix always. And the effect is that it blocks ligature of neighboring characters. So this is the same word, Felestiniha, sorry for my pronunciation, which means pencils, written with the zero with non-joiner here, or without it. Without it, the Arabic letters are supposed to merge together and it would look like this. But because this ha is a plural suffix, it is supposed to be written this way. And that means that they have to insert the invisible zero with non-joiner here, which is important if you look at the character sequences programmatically. So you have to know about it. And it's not a letter category, it's other. So fortunately, it is possible to query the character categories in regular expressions. So I have excerpts here of syntax from Perl, which has categories. So there's a /p and then L means letter, and LL, I think it means letter lowercase, and it's letter modifier and letter other. And this is the mark, I guess. And you can have a similar regular expression extension in Python as well, but it's not available there by default. So you would have to import regex and use it as the regular expression engine. But it's a third-party module, so you would have to install it first if you don't already have it. And then the second interesting thing, mainly for diagnostics, debugging, is to be able to find the Unicode character names. So because the languages have modules where the entire Unicode database is available, so again, you can query them. So in Perl, you would ask use car names, and then you can provide a character or character code, and it will tell you the Unicode name of this character is Latin small letter n preceded by apostrophe. The names are always sequences of just uppercase English letters so that they are visible in most encodings, even if you don't have Unicode. And you can get the same behavior with a different syntax in Python as well. So that is sometimes useful, especially if you suspect that your sequence of characters has something weird in it, and your editor, your font will not reveal it. Then you can translate the sequence to the names of the characters, and then you will see that maybe there is this zero with non-joiner which you were not aware of. Here is an example of what may happen, why it is important to be able to find what the characters actually are. Here it looks like we have Russia written in the Cyrillic letters, but in fact, which you wouldn't be able to recognize just by looking at the glyphs, the second and the third character are not Cyrillic. They are the correspondingly looking Latin characters, but they look the same. They shouldn't be there. There should be Cyrillic characters instead. But Unicode, for compatibility reasons, has different blocks for Cyrillic and Latin. So there's twice the same character, even if it looks the same. And sometimes if people type it on a foreign keyboard, it can happen that they mistakenly use a letter from the different alphabet, and they type English instead of Russian, even though they wanted Russian. There are more surprises like that, even some more exotic ones, like here the first exclamation mark, or what looks like an exclamation mark, is actually a click letter from I think that's an African language. So that's a sound that I can't even pronounce. But again, because it's a sound and it's not just the exclamation mark, it has to be encoded as a letter and not as punctuation. And my final point that I want to make is that, as you've already actually seen, sometimes it's possible to encode the same character in different ways. In some cases, so far I was showing you that these were actually different characters that just look the same, but there are also examples of two different encodings that really mean the same character. So there are multiple ways of encoding the same thing, and this is dangerous, especially if you use the text data to train a model in machine learning. You need to make sure that the same thing is always encoded the same way. So you have to be aware of this danger of Unicode, and you should always normalize Unicode in your data. So there are actually routines available for that. You don't have to implement it yourself. I will show you that will be my last slide. But there are various types of Unicode normalization, because there are various types of similarities or equivalences within the Unicode character set. So the examples that I'm showing on this slide are called canonical equivalents. And those are really something that should be considered the same thing, the same character. So for instance, the Turkish ch, the C with the Cedilla diacritics below, can be encoded either as one character, which has its own code point, or as a combination of the base character C and the combining diacritics. And don't be confused by the different shape of the diacritics here. It's just because I had hard time to making it visible using LaTeX and Beamer. So I used a different font. But the result would really be the same if we had the same font. Or sometimes you have two diacritics on one letter. In some languages, this is possible, like Yoruba in Nigeria. So this is not from Yoruba, but you might have one dot above the letter and one dot below. And then again, both of them are combining. So you have three code points together that will give you the actual shape of the letter. And it doesn't matter whether you first show the dot below and second the dot above, or vice versa. So the result will be the same, because these circles stand for 0 with character. They just really combine with the previous letter. So this should be considered the same thing. And we want to make sure that we will always have canonical ordering. And there are similar problems with Korean alphabet, which I don't know too many details about. There are also equivalences like the letter omega from the Greek alphabet versus the same letter that appears in the set of mathematical and physical symbols, where it is called the ohm sign. But again, I have different fonts here, but otherwise they are really equivalent. So we want to make sure that these will be encoded the same way. There is another level of equivalence, or this is not actually equivalence, this is rather relation between characters. And this one is more tricky. So we don't always want to unify these characters. So this is just an example from the Unicode website to show you that not everything, every correspondence between characters is the real equivalence, but the previous one is. So, pardon. So this is what Unicode defines based on those categories. They define canonical decomposition and canonical composition and compatibility decomposition. That would be according to the second slide, and this is not of much interest to us, but the first one is. So the highlighted one is what we should always do in order to get the canonical form of each character. canonical decomposition followed by canonical composition, which will reorder the diacritics and everything. And here is how you do it again in Perl and in Python. So fortunately, there are modules that do it for you. You just have not to forget it when you are processing data. Last word of warning, because these modules obviously rely on large Unicode tables that they have somewhere stored in the system. If you get a different version of Python, you might get a newer version of Unicode, and there might be some new characters, or some of them might be redefined. So you might get slightly different results. So be aware of it. Okay, that's all I had to say today. So let's stop sharing. And Rudolf, it's yours.